Okay, ladies and gentlemen, chapter 10 is about what we call sequences and series. Sequences is a list of related values. How are they related? Well, in many different ways. So there are a few common types of sequences that we'll discuss, but some are just oddballs and unusual. So that's the definition of the term sequence, a list of related values. A series is a running sum of those related values. So here I give you an example sequence, and here it's series. So the series is the sum up to a certain point. It could also be the infinite sum. So the first series for that sequence is just 6. The second is 6 plus 9 or 15. The third is 12 plus 9 plus 6 or 27, and so on. So a series is when you add up every term up to a certain point. And to use to express a series, we sometimes use what's called sigma notation. And I give you an example of a bounded sigma notation. It's that big funky E, which is actually a capital sigma. So there's several types of alphabets in the ancient world. Almost all the alphabets in the Western world are derived from what they call linear A or something like that. Maybe the English teacher could explain it better, but this is one of those derivations of linear A, the Greek alphabet, and here's the capital sigma. All right, so I equals A. This is the point you start. So you'll start at the 8th term, which could be 1, could be 10, whatever. And then you'll stop at the B term. So this is the starting point and the stopping point for the summation as far as the terms are concerned. This is the expression that defines this sequence. So in this case, it would be 3 plus 3n if we start at 1, or 6 plus n if we start at 0. So indexing can also change the way we express these. All right, questions about anything? Okay. Yes, sir.
So that sigma notation is only for series?
Yes. Okay. Used to express series. It's a fundamental idea in calculus because you can't get the integral, which is the second big calculus mechanism, without a summation. So once you get, and it's a big thing in Cal 2. So when you get to Cal 2, man, oh man, are you going to do some summations? Sequence is an ordered list of numbers, and you can have a finite sequence, or you can have an infinite sequence. In other words, it could go on and on forever, or it could have a certain number of terms, and each individual element in the sequence is called a term. So they can be finite or infinite. Finite ones are boring. We don't do a whole lot with them. Infinite ones are more interesting. There's a lot more mathematics we can do with an infinite list. Out of curiosity, how many of you guys are planning on a Thanksgiving get-together? Just be careful. My mom was nervous, so we're going to do a Zoom call. It's kind of lame, but we'll have a Zoom Thanksgiving. I'm going to put tablets up at all the places around my table. I am really. If it were up to me, we just have a regular one, but I defer to my mom in that case. So ways we can define a sequence. We can have an implicit definition, which is just a list, like so. Or we can have an explicit definition, which is a function and some other conditions that are set, and we can make a list from that information if we needed to. So implicit, just a list, explicit, function. Okay. Yeah, that's correct. So let's do some practice here with infinite sequences. Practice finding the next four terms. So you're looking for the mathematical pattern. And some people just have a head for this. They're just innately good at it. I can't really teach you to do it. So some of you will just have the skill where you can look at it and predict what comes next. Some of you will not. And so I remember I had a professor in college, and he taught analysis, which is a senior level math major course, really intense. You do these proofs. Man, he worked in a room that had a blackboard that went all the way around the room, and he would often fill all of it. So by the time he got, and that was before smartphones or, we had to write that junk down, so this guy had some mathematical skill, but he sucked at this. So whenever we ran into a situation like this, he would call a fellow professor, his name was Anant Godbole, and he'd say, hey, what's the nth term? And Mr. Godbole, Professor Godbole, Dr. Godbole, would say 2 to the n plus 3n. And, he'd be right every time. He just had a head for it, man. So some people can do it, some people can't. Randall, tell me what comes next on A.
22.
Good. And then? Good. And then? Good. And then? And then just I guess you guys never saw the movie Hey Dude, Where's My Car? With Ashton Kutcher, early 2000s comedy. That was a joke reference from that movie. So first one was easy. And in fact, this is what we call an arithmetic sequence, which we'll get to more tomorrow. But it's one where something is added or subtracted to each subsequent term. In this case, we're adding 5. This one's a little more complicated. Isaac, what do you think comes next?
6.
I would agree. Now, there's no way to know for sure because we don't have an infinite amount of information here. But it's +3, +5, +7. So it would make sense that the next one would be +9 to me. And then what, Isaac?
27.
Yeah, +11. And then what?
52.
Well, I would say 50 +13. You see what? It's the next odd number. It's what I think it does. And then the last one, 65. So +3, +5, +7, +9, +11, +13, +15. We're just guessing. That's the pattern that it looks like. So finding the next 4 terms here. Now this one is defined explicitly. In other words, we've got a function. So let's figure out these. First of all, a sub 1, I just plug 1 in for n here. So 2 times 1, and then times -1 to the first power. So 2 times 1 is 2, -1 to the first power is -1. So that'll be -2. Don't forget PEMDAS. Do the exponent before you multiply there. So 2 times 2 times -1 to the second power is 4 times a +1, 4. And then 2 times 3 times -1 to the third power is 6 times -1, or -6. Predict what comes next, Mason.
8.
Good. See why he got that? He saw the pattern. Change the sign, it goes up by, absolute value goes up by 2. And it changes sign. That's correct. Okay, so finding the next 4 terms. Oh, that wasn't very helpful. Finding the next 4 terms where it is defined implicitly or explicitly. Any questions about that? That was the learning goal we just addressed. Okay, so there's one more way to define a sequence. It's called a recursive definition. This is when one or more initial values are set, and then the rest are defined explicitly. So it's kind of like a mix of implicit and explicit. You've got a few defined in the beginning, and then a formula for the rest. So here I say the first term or the 0th term is 3, and every subsequent term is the previous term plus 17. So this is a recursive definition. It depends on one or more initial states. So I can't have it depend on the term that came before without defining at least one term. In some cases, they depend on more than one term that came before, including the most famous one of these, which we'll talk about next. The first great mathematical work of the Enlightenment. First mathematician to rival the classical thinkers like Euclid and Archimedes and Hypatia. First great female mathematician that is known to history. I'm sure there were many others. Okay, so let's find the first 4 terms here. So this will be f sub 0, and it's fixed at 3. And every subsequent term is the previous term plus 17. So that's 20, that's 37, 44, 54. And this would be 1, 2. We can index this however you like. F sub 0 is just a starting point. Doesn't have any algebraic significance. Just like subscripts are like a last name for the variable. They indicate no mathematical operation. Questions about that? 3 ways to define a sequence: implicit, explicit, recursive. And the most famous of all recursive sequences is called the Fibonacci sequence, which is recursive. You got f sub 0 as 1, f sub 1 is 1, and then every subsequent term is the sum of the previous 2. And it's really interesting. Fibonacci came up with this by observing the breeding habits of rabbits. Rabbits, notoriously prolific breeders. And so they're basically, all the females are always pregnant all the time if you have them around the males. So if you've got one female rabbit, and he imagined a perfect scenario where all the rabbits were female and they were always pregnant as soon as they could be. So rabbit has to be a month old before it can get pregnant, and then it has a month gestation period in this scenario. So for the first month, you've got the one rabbit that can't get pregnant yet. The second month, now it can get pregnant and is, but it's still just one rabbit. And then the third month, it'd be the sum of the previous 2. And so f sub 2 is 1 plus 1 or 2. F sub 3 is 2 plus 1 or 3. F sub 4, 3 plus 2 or 5. Each subsequent term in the Fibonacci sequence is the sum of the previous 2 terms. And Fibonacci numbers play a very interesting role in evolutionary biology. So it was just coincidence that Fibonacci chose a natural thing to try to model mathematically. He would have, anything he came upon, he probably would have applied mathematics to. He was a very mathematically minded person. An Italian Enlightenment mathematician. Wrote Libra Bocce that was published in the 1200s, if I'm not mistaken. And it was the first mathematical book published basically since the classical age. So the entire Dark Ages, we really did no substantive work mathematically in the Western world. We just worried about religion for those periods of time. So anyway, he just applied mathematics to everything, and he chose something from the natural world, and he happened upon something that models a lot of things in nature, the Fibonacci sequence, because evolutionary biology is iterative. The way it works generally is to add to whatever's there already on your DNA. And so things like the number of protrusions from a central body, we've got our trunk, right? Got 2 legs, 2 arms, and a head. That's 5 things sticking out of our trunk. That's a Fibonacci number. If you look around in nature, you'll see almost exclusively Fibonacci numbers. And it also, your book has a cool example where it uses the branches of a tree. So what happens with the branches of a tree? If you have a single, of course it comes out and it's just a single branch. And then after the 2nd month, it will be preparing to bud. And then on the 3rd month, so month 2, start with 0, then 1, then 2. So after 2 months, you're going to have 2 branches. So another one will grow out here. But he's fresh, right? He can't bud again. But this other one, he's ready to go again, you see, because he's already had his 2 months. Ungroup those. And then on the 4th month, so now this one and this one are ready to bud. Sprout a new branch. This one not quite yet. And of course my drawing's terrible, but you guys get the idea. 1, 2, 3, 4, 5. So you see how these are Fibonacci numbers? And it would go on like that. And so you can predict the number of branches, again, assuming everything is ideal. Nobody's come along and cut them off, or the weather's not preventing it from growing normally, things like that. So assuming everything's ideal, you'll have a Fibonacci number of branches every one of these months. Of course, it will eventually hit a point where it's not advantageous to grow anymore, or it's out of its growth cycles. But assuming it's in a growth cycle, every environmental condition is perfect, you'll get these values. Here's another interesting thing about the Fibonacci sequence. So if I were to go on and on and on with these numbers forever, in other words, I would take the limit as n goes to infinity of a Fibonacci number divided by the previous Fibonacci number. So if I divide a Fibonacci number by the one that came before, it approaches a very interesting constant value. And we call that value phi, which is this Greek letter. And it's about 1.618. So 1.618 is an approximation. We call it the number phi, which again is this funky Greek letter I've written here. Neat thing about phi, it manifests in nature all over the place. So if I were to measure your arm from the shoulder to the elbow and then shoulder to the fingertip and compare those ratios, I would get something really close to 1.618. If I were to take the most classically beautiful people and measure the y-axis of their face divided by the x-axis of their face, I would get something very close to 1.618. If you take the chambers of a nautilus, you know what a nautilus is? It's a big old snail creature that lives in the ocean. So if I were to take, and its shell is kind of like this. So if I were to take any of those chambers versus the next chamber, I would get that ratio of 1.618. So, and it's not just plant life, or it's not just animal life, it's plant life, it's bacteriological life. Over and over and over, this funky number keeps coming up in the analysis of evolutionary biology. So 1.618 is some essential value with relation to DNA and evolutionary biology. Scientists haven't quite got it figured out, but this is important somehow in a way we don't yet fully understand. The Fibonacci sequence. So let's try to find the 5th term here of this explicitly defined sequence. So here I'll say a sub 1 is 1, and then each subsequent term is the previous term plus 2 times the n value minus 1. So a sub 2 is going to be this previous term plus 2 times 2 minus 1. So 1 minus 1 is 0, and then left with 4. And then the third term, see, I have to build these up. I can't just know the fifth because it's recursive. I have to go through the list in order. Unless I see a pattern, like Mason did earlier, then maybe I can predict it. So from 1 to 4. And then the third one is going to be 4 plus 3 times 2 minus 1. So that's 4 plus 6 minus 1, which is 3 plus 6, or 9. So 4, 9. Any predictions on this next one?
16.
Good prediction. So that's 4. Yeah, I just put the 2 outside the parentheses. Otherwise, it's going to be confusing. So 9 plus 8 minus 1, 16. Any predictions on the next one?
36.
Close. You're on the right track, but you skipped one. Good prediction. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, maybe, I don't know. So this would be the previous one, which is 16, plus 2 times 5 minus 1. So that's 16 plus 10 minus 1, 26 minus 1, or 25, as we predicted. So the fifth term is 25. I think this eventually deviates from the perfect squares. If I remember this right, eventually it makes a mistake, but certainly for the first 5 terms, it's correct. Okay, so finding a certain value from a sequence, different ways to define a sequence, how the Fibonacci sequence is related to nature. Any questions about any of that stuff? Sir?
Is there like a recursive sequence for prime numbers?
No. And if you find it, Isaac, you'll win a Fields Medal, which is the highest honor you can have in mathematics. Mathematicians are not given Nobel Prizes because the original person that created the Nobel Prize despised mathematics. Because of his ineptitude at least that's the story that is told. So mathematicians have their own thing, and it's called a Fields Medal. And I tried to do this in college. Actually, kind of a funny story. Exactly what you just said. I tried to create that formula. I tried to induce it from data. So, you know, like the first prime is 2, second prime is 3, third prime is 5, and so on. So I made these lists of ordered pairs. And I tried to see if I could interpolate a polynomial of degree n. So if I had 20 points of data, that would be a 20th degree polynomial. And I wanted to know if I made one of those big enough, would it start to approach the next prime number? In other words, theoretically, was there some list of primes long enough that would allow me to interpolate a polynomial that defined the primes? And if terms started dropping out, I would know I was on to something. So I wrote a computer program to do this. I went into ETSU's computer lab, and I put it onto their computer, and I pressed enter, and every screen in the room went dark. I politely packed my bags up and walked out. So I crashed all of ETSU's computers one day trying to do this. I don't dare try to do it on a home computer. It's not nearly powerful enough. But good luck to you, sir, if you take on the same challenge.
Why did it not work?
Too much computing requirement. The computers were not strong enough to do it.
Does it mean it could be potentially correct?
If my strategy would work, yes. Somewhere in Elon Musk's basement is a computer that could do it. But it's not currently available to the public, at least as far as I know. Quantum computing, I think, will be the key. Once you have, it'll probably be in the later part of your life, quantum computers will be available to the public. I think then you could induce a polynomial, if such a thing exists, to predict the next prime. But that's one of the, we talked about the white whale from Moby Dick. Formula for primes is the white whale of most. thing that they want to do but can't quite get. So a sequence can be said to converge, in other words, approach a certain value as n goes to infinity. As the term gets larger and larger, it's going to get closer and closer to a certain value. Or it can be a divergent sequence, which does not approach a certain value. It either goes to infinity or bounces around up and up, above and below the x-axis, or has some other behavior that's non-convergent. You remember that book series? You guys old enough to have read those? Divergent. Do you remember those, Em?
Almost familiar.
Isn't that always the case? I think a person has a good imagination. They'll never get from a movie what they will from a book. But who knows, eventually when we have like VR movies that you actually interact with, maybe that won't be the case. Maybe the opposite will be true. So let's ask ourselves, convergent or divergent? Let's find some values and see. So a sub 1 is negative 3 times 1 plus 12, which is negative 3 plus 12 or 9. A sub 2, negative 3 times 2 plus 12 is negative 6 plus 12 or 6. A sub 3, negative 3 times 3 plus 12, negative 9 plus 12 or 3. We see where this is going. It's going down 3 each time. So 1 goes to, actually 0, if we have a 0th term, that would go to 12. 1 goes to 9, 2 to 6, 3 to 3, and 0, and so on. So we see this is going, like my inexact points, in a straight line downward, where it will continue to go on and on and on to negative infinity. So this, ladies and gentlemen, is a divergent sequence. It diverges to infinity, in this case, negative infinity, as n goes to infinity. And so for this next one, I've already got some points to find here just to save us some time. But it is negative 1/2. Well, it's actually recursive. So a sub 1 is 36. And then each subsequent term is negative 1/2 times the previous term. So we see these values are what would result. Let's plot them and see what we get. So 36 for 1. 2 is negative 18. 3 is positive 9. 4 is negative 4.5. And then positive 2.25. So do you see how this one's going to have this sort of behavior? And it will approach 0. So this will converge. This is a convergent sequence. Because as it gets closer and closer to infinity, it gets closer and closer to 0.
Does it ever get to 0?
Yes. Well, because of its, actually, no, it won't. Because this line is to help us understand. It's not really the way it works. This only works when we plug in integers, typically, for a sequence. The input would not be fractions. So the values in between where it would actually cross the x-axis don't technically exist as a term. And so, no, it'll get closer and closer and closer, but never get to 0. But we still say the limit as n goes to infinity is 0. So its limit is 0. It will actually never assume that value for any integer you choose. You can choose a quadrillion, and it'll not quite be 0. Good question. Other questions, ladies and gentlemen? All right. Convergent versus divergent. So a series is the sum of all terms in a sequence. I've got a finite. You can choose a certain finite number of terms to sum, and that would look like this. Could be infinite, and it would go on and on forever. And sometimes infinite sums are defined in some very interesting cases. We'll get to those in part 3, I think, is when I do some of those. But the nth partial sum is the sum of all values in a sequence up to the nth value. Let me ask you guys a question. Have you ever had this experience? You interact with someone and they say or do something that indicates such a high intelligence, you're just blown away. Have you ever met somebody whose cognitive capacity was just unreal? They solved a problem that you've been fumbling around with or whatever. So you interact with this person and you're like, wow, that is a freaking genius. So this has happened to me a few times in my life, but never quite to the degree I'm about to describe to you. So this was a case where in the 1800s, and so stories about this vary a little bit. So this is a time long, long ago, 200 plus years ago. In Europe, I think Switzerland, there was a little student named Carl Gauss, and he was in his elementary or grammar school classroom, and all the kids had their little slates, you know what I'm talking about, that they would write on the chalk and then erase and compute more and so on. So the task given him by his teacher was this: start adding up numbers from 1 to 100. In other words, 1 plus 2 plus 3 plus 4 plus 5 and so on, all the way to 100. And I'm sure at this point the professor put his feet up, got out the newspaper, and anticipated a nice long rest while the students laboriously tackled this problem. Well, one little student named Carl Gauss walked up to his desk almost immediately. And I could just see this in my mind. I imagine the professor's like, this little idiot didn't even understand what I asked. And so Carl Gauss showed the professor the slate, and he had 5,050 written on it, which is the right answer. So the professor was baffled. It'd only been seconds. He had given them a problem only seconds before. And so he said, how the heck did you figure that out? And so Carl Gauss said this. He said, well, I realized that you had 1 plus 2 plus 3 and so on, all the way up to 100. So he said, I realized it would be equivalent if I did it like this. Do you agree with little Carl Gauss? If I add up this bit to that bit, it'll still be the same thing as this. So this is just the first half and the second half. But here's the genius of Carl Gauss. What's 1 plus 100? What's 2 plus 99? And so on. They're all 101. And how many of them are there? So he just said 50 times 101 equals 5,050. Game over. Took him seconds to do this. There is now a formula that we use for the summation of an arithmetic sequence that involves this same work of this little 6-year-old child from this grammar classroom. Carl Gauss went on to become what was called the Prince of Mathematicians, one of the most accomplished mathematicians in the history of our planet. So his genius was fully realized. Fear not. He was, to the credit of his professor immediately funneled him to a university where I think he graduated from the university when he was like 12 or something. So pretty exceptional person. Did a lot of work in magnetic and electromagnetism, other stuff. Anyway, so solving this problem using this method always struck me as a really interesting related thing to the series, because we're making a series of these, aren't we? Okay, so let's do some partial sums. So the fourth partial sum of a sub n equals -2 to the nth power plus 3. the fourth partial sum. So we need to find all the values up to that point to begin with. So let's find a sub 1. That's going to be negative 2 to the first power plus 3. So that's negative 2 plus 3, or 1. For the second term, it's negative 2 squared plus 3, which is 4 plus 3, or 7. And then for the third one, negative 2 to the third power plus 3. So that's negative 8 plus 3, or negative 5. And then the fourth term, negative 2 to the fourth power plus 3. So that's going to be positive 16 plus 3, or 19. So the fourth sum is going to be 1 plus 7 plus negative 5 plus 19. So that's 8, 3, 22. And we can test our answer with a calculator. Looking around here, show me all your calculators, guys. I think all of you have got ones that will include the summation. Yes, I think so. I'm not sure about papers. I think so, though. I think they all have it. That's just a model I'm not super familiar with. We'll test it, and I'll show you guys. So if I want to find this on my calculator, I need to convert it to sigma notation. So writing this same problem in terms of sigma notation is going to be like this. From n equals 1 to 4, negative 2 to the n plus 3. So that's how I would write the same problem, excuse me, in sigma notation. So let me see if I can pull this up on my camera, and I'll show you how to do this on your calculator. There we go. Okay, so if you hit math and then navigate down, you should see summation down there at the bottom. So hit that summation, and then we're going to define this. So from, just use x from 1 to 4, and I think it was negative 2 to the x power. Is that right? Yes, plus 3. Actually, I need to put that inside parentheses because negatives don't really behave otherwise. There we go. And then plus 3 or plus, oops. Plus 3, yeah. All right, so we get the answer 22, which confirms our previous result. If you don't have summation on your calculator, rip, you got the wrong model, it won't do it. There is actually a way to download that functionality to your computer. See some of you guys squinting here. Maybe I can help you out. All right, so that's how to do it on the calculator. If you have that functionality, not everybody will. But I think every calculator I looked at just now should have that. So partial sums. Sigma notation. So sigma notation is another way to describe a series. As I just showed you, it's a way you can put in your calculator. Here's a couple examples. And yes, it can be infinite. And some models of calculator can actually handle that. The TI-89, which I used extensively in college, dealt very well with infinities. So sigma notation. as we discussed in that introductory definition slide, way to describe series. And here we have a starting point, a finishing point, and the definition of the sequence with respect to the input values. Now, you can't use this with the type of sequence definition that's just a string of values. You can't use it with a recursive definition. You must have an explicit formula, an explicit definition in order to plug it into a summation notation. Now, sometimes you can rewrite them. So if I were to say, I wanted this one, let's say 3, 8, 13. So 18. So I could rewrite this as a sub n equals -2 plus 5n. So if I plug in 1, I get 3. Plug in 2, I get 8, and so on. So sometimes you can take this implicit and rewrite it as an explicit, and it'll still work with this. But you need an explicit formula to plug into the signal. So here's the old Carl Gauss problem. Let's test it on our calculator and see if old Gaussy boy was right. So on your calculator, go to math, go down to summation, type in x equals 1 to 100 for x. You should get 5,050. The same result we just discussed. Just x. It's not there. You're in radian mode, so that's good. Or polar graphing mode. If you're in polar graphing mode, theta is very good for you. Everybody figure it out? All right, ladies and gentlemen, let's do a couple more of these. And I'll do this one by hand. You know, I like to make you at least endure one by hand. So, from 1 to 5 for this. So a sub 1 plus a sub 2 plus a sub 3 a sub 4 plus a sub 5. A sub 1. If I plug in 1, so that's 4 times 1 minus 3 plus 4 times 2 minus 3 plus 4 times 3 minus 3 plus 4 times 4 minus 3. Get myself just a bit more room here. And finally, 4 times 5 minus 3. Plugging into that. So that's 4 minus 3 are 1, 8 minus 3 are 5, 12 minus 3 are 9, 16 minus 3 are 13, and then 20 minus 3 are 17. Going up by 4 each time is what's happening. So if I add all these together, 1 and 5 is 6, plus 9 is 16, plus 13 is 29, plus 17 is 46. And we can, of course, check this with our calculator. So let's do that real quick. Yes. Oh, it says 45. Let me see where I messed up here. That's 15, 28. Yeah, okay. So, my bad. Mental arithmetic can get you. That's why it's good to use a calculator, ladies and gentlemen. To at least double check yourself, lest we have a disaster. So this next one, I can't possibly calculate by hand. Look what this upper bound is. So there are some tricks I can use to understand what it would be by hand. So 7 over 10 to the n, that would be 0.7. And then 7 over 10 squared would be 0.07. So do you see how this would just be, and then 7 is repeating? So I know that is 7 over 9. But there are some calculators that can do it. And a way to really get close in your calculator is just to type in a huge number. So let's see what happens when you do that. So summation from x equals 1, put in like 3,000 or something up there, of 7 divided by 10 to the x power. Might have to think about it a pretty hot minute. And I just overflowed my calculator. Depending on your RAM, it may or may not like it. So an alternative, when the TI fails, is good old Wolfram. Wolfram can make short work of this problem. At least I hope it can. Don't let me down, Wolfie. So we want the sum of 7 divided by 10 to the x power from x equals 1 to x equals infinity. Yep, got it. Does this make sense to you guys, or does that just look like craziness? Computer programming is my hobby, so that kind of stuff's second nature to me, but yeah. Okay. Questions about anything we've talked about? Or thoughts or comments? In that case, your task is page 595, 2 through 16 even. Excuse me. Also, don't forget to take the practice test before Thanksgiving break. I will be on there checking it, trust me.
Will we be able to use this kind of calculator on the test?
No. I will, well, the best option, because you'll have a computer in front of you, is to use a computer-based calculator, but technically graphing calculators are off limits. Now you can, hold Control Enter, type in calc, and then this comes up. So you could do a lot with this if you practice. I've got it frozen. You can do a lot with this if you practice. So we'll be practicing with that entire week. But unfortunately, no graphing calculators.
Why is that?
Well, it's an interesting question, and I can only speculate, but my speculation is this, that a lot of the people that write this test are part of what's called the College Board. And as I said, they're a notoriously anal retentive group of people worried to death about rules and regulations and so on. And I think most of them, at least the mathematicians among them, came up during the 60s and 70s when technology was not used. And they're sort of dogmatic purists in that respect. They think if you're not writing it down, then it doesn't really count. And so you must do it the old-fashioned way. You must earn it. So I think that's my speculation, and that they feel that there's no other legitimate reason. So, but they are imbued with the power to make that decision. They have decided not to allow it. Most unfortunate. All right, ladies and gentlemen. Cut this off.